Okay, so I'm going to draw on a very classic, a study built on a very classic meta-analysis. One of the really classic meta-analyses, and I think I have it in here to take a look later, was whether statins prevented heart attacks or not. And in this particular case, now that people were able to conclude that statins worked, right? They were able to ask the next question, which was about dosage. So in this study, they compared a high dose versus a moderate dose of statins to reduce heart attacks, cardiovascular disease. So this is what's called a forest plot, okay? And it is a graphic display of the main results of a meta-analysis. And if you've read meta-analysis in most biomedical journals, they're going to have something that looks fairly similar to this. Okay? Okay, so first you have the study name, and I did not make these study names up. These are actually the names of the studies in that meta-analysis. For each study, we report the study name, the risk ratio, okay, of people getting the standard dose versus getting the high dose, the number of people in the study, and the relative weight the study got in the whole meta-analysis. If we ignore the graphic effect for a minute and look at the p-value, we can see that of the 5 studies, only 2 of them, of the 4 studies, the bottom is a summary, only 1 of them had a traditionally statistically significant effect. Okay? But if we look at the summary meta-analysis, another interesting thing here is if you actually look at the risk ratio from study to study, it is fairly consistent, right? And so it stands to reason that the differences in p-value are not a good indication of the drug's actual effectiveness. Okay? If we look at the summary, it is 0.85 with about 27,000 patients, and in all the cases, we can also see in the graph that the high dose is favored compared with the standard dose. Okay? And you can, well, I'll wait for later for the rest of that. That's enough information to absorb. Okay? So the effect size is information that tells us about the degree of relationship between the treatment and the outcome. Okay? In this case, it's based on proportions. It's binary data, but it could also be based on a comparison of means. It can be based on correlational data for observational studies, and so forth. And the weights that you see assigned to each of the studies, as I mentioned before, we want that to be based on the information value of the study, which is closely related to, but not identical with, sample size. Okay? So if we look at the graph here, the size of the box in the middle represents the weight of the study, and the long lines represent the confidence interval. This brings home an important statistical point, which is that sometimes studies are not significant because a little tiny part of the confidence interval goes over the line of no effect. Okay? But the larger the study, the more weight, the smaller the confidence interval, and if you look here, you can see that there are largely overlapping confidence intervals from study to study. Another hint that the effects are really pretty consistent from study to study. The summary is really a weighted mean. It's the average, the average effect of each study multiplied by the weight. The confidence interval is based on the standard error, the same way it would be in a primary study. And the only difference is that it takes into account that we're now doing 2 levels of sampling. One is the sampling within the studies, and the second one is that the studies are hypothetically a sample of a larger population of studies that could have been done on the topic. Okay, this triangle, or diamond rather, represents the summary effect and the confidence interval of the summary. The confidence interval of the summary is smaller than the confidence interval in any of the component studies because of the larger sample size. Therefore, we have a more precise estimate of the mean effect. Okay.
Can I ask a question?
Yes, ma'am.
I can see that p-value is 0, and I assume it can't be 0, so it's just...
It just, we truncated it.
But is it okay to put it like this? Because I usually...
No, it isn't. It was bad of us to do that. Right. It should say less than 0.00 or something. Yeah, and I really, I tend to think that after the second decimal point place, it doesn't matter that much. You know, we get very hung up about it. But yes, it shouldn't be displayed like that. That was wrong. But you can see it's very, very small. So let's just go back here. So what we want to look at is the study, all the included studies, each study separately, their effect size estimate, the weight that they carry in the analysis, a graph of the individual effect size and its confidence interval. We can also look at the power of the study, and in this case you can see very clearly again that power is very closely related to whether the study was significant or not. Okay, because if the effect size is the same from study to study, right, then the p-value is going to be positive, significant or non-significant, essentially just based on the power of the study. You can see that these 2 studies with the largest p-values have the lowest power to detect an effect size, that the one that was in the middle here was closer to significance, and that once we had a 70% power, we achieved statistical significance. With 83% power, it's literally off the charts. And the typically, have you learned anything about power analysis? Yes? No? No. Okay. Power analysis basically tells you prospectively how many subjects to plan for in your study. Okay? And the answer is not however many I can get my hands on, which is usually the real answer. But in terms of study planning, you want to give yourself a reasonable shot at being able to find a statistically and clinically meaningful difference. And so you plan your study, or you should be planning your study, to have power of about 80% to detect the smallest effect that you would consider clinically meaningful. Okay? People often fall short of that goal and they start tricking themselves by doing things like saying, oh, I really expect the effect size to be bigger than that, so I don't really need as many subjects as this ridiculous computer program just showed me. But if, in fact, your first guess about the effect size is right, and then you run your study on fewer subjects, then you really need to be able to find the effect you're looking for. You're having your chances of finding the effect that you're looking for. So power is simply the probability that you will be able to declare statistically significant the effect in your study. Okay. It's the opposite. Okay, and while we spend a lot of time worrying about type 1 errors, we don't spend as much time worrying about type 2 errors, which is our inability to declare an effect significant when it's really there. And that's what power analysis is all about, making sure that we keep down our type 2 error rate as well as our type 1 error rate. Since very often primary studies are not particularly good about keeping down that type 2 error rate, one of the purposes of a meta-analysis is to be able to have sufficient combined power to be able to identify effects that are actually there. So in this study, if you were the doctor, okay, would you want to use, all else being equal, would you use the high dose or the standard dose? How many people say high dose? Come on, you gotta raise your hands at least. Or how many people say the standard dose? Okay. Why?
Because they have a lot of side effects.
I said, well, everything else being equal, but okay. Side effects are a legitimate concern, okay? But so this data, I think, these data show pretty conclusively that if we're just looking at the outcomes of death and heart attack, not thinking about side effects or other possible adverse outcomes, we would want to go with the high dose because the risk ratio is 0.85. When you think about all the people who could be put on this kind of therapy, that adds up to a lot of lives. If we were doing a narrative review, though, chances are we'd say 3 of the 4 studies produced insignificant results. Therefore, either we don't know, or even maybe the treatment doesn't work. Not going.
Maybe this is not a very polite question, but when I look at these numbers, everything is clear and you put it perfectly. But then when you look at the ends, these 27,000 people, roughly, what is the NNT? How many people we should treat with high dose to get one? Isn't it very high? Regardless of the fact that it is very significant.
Well, it's not the question of very significant. It's more a focus on the risk ratio. And you can actually, not directly with the risk ratio, but I think if you took the risk difference, then you can kind of put it into an equation to figure out the number needed to treat pretty easily. I'm not an expert on those formulas, but when we talk about binary data, you'll see that having the data in this form makes it a lot easier to estimate the number needed to treat. And you're probably right. It's probably a lot of people. But when you consider how many people overall are at risk and need the statin, this kind of therapy, if we summed across all the countries where statin therapy could be given, you're still going to save a lot of lives, even if you don't really increase even if you have to treat a lot of people to save one, there are a lot of people being treated.
But then we come to the issue of the money.
The money and the side effects and those kinds of things. Yeah, but that's why I'm a methodologist and not an economist and health economist. Okay. Those are very good questions. They're important clinical questions, but they get into decision making. One of the earliest criticisms of meta-analysis is that you can't really reduce a complicated question to a single number. And if I were good at voices, I would put on my best Inspector Clouseau voice from the Pink Panther and say, but that is not our question. Okay? So the point that I want to make is that the meta-analysis doesn't just focus on the mean effect. It doesn't just focus on producing some magic single number. But that it's truly a synthesis, which means we need to look at the variability and robustness of effects, as well as what the average effect is. Because you can all imagine situations where the average effect is positive, but a third of the cases have a negative effect. So knowing the mean without, just like in a primary study, you wouldn't really find the mean very informative unless at least you knew something about the standard deviation and so forth. We really don't want to just know about the meta-analytic mean, but we really want to answer the question, how well does this mean sort of speak for or represent the distribution of effects that it comes from? Okay. We need to know about the variability in effects in order to be able to answer that question. I want to emphasize the point that the way you do the synthesis is going to be primarily affected by the question you ask. So you need to ask the question correctly and unbiasedly, because there can be bias in questions too. I think Peter Tugwell sometimes points that out, that we bias things just in the way we ask. The way we analyze our data, or the questions we ask of our sample of studies, is also related to our research question, and our conclusions depend on our research question and also the information available. So just like the psychiatrist asked, well, what happens if, small studies with very different populations? Well, sometimes meta-analysts really don't find the primary studies that are needed to answer the question they would like to ask. And so there's, first of all, such a thing as called an empty review, which basically you say, yeah, this is a good question, but nobody's really answered it yet. At all, even in any primary studies, where nobody's done any decent studies. And decent doesn't mean you agree with the conclusion or not. It just means that the study had certain methodological characteristics, and including perhaps population or setting or something. Sometimes some people have done studies, but the information is still pretty sparse, and so we have to really couch our results in a way that reflects the uncertainty. So one of the things that, one of the unique features of a meta-analysis is that it really provides a context for understanding the results of primary studies. And we can imagine three different types of bodies of literature, or three different types of answers that we may find. We can find that a treatment, the effect of a treatment is really consistent across a whole group of studies, even though there were men and women, old people and young people, people from Western cultures and people from Eastern cultures, people from teaching hospitals and people from urgent care centers, that the effect is the same across all of those settings. Or we could say, well, the effect is different from setting to setting, and we can tell that in ways that I'll show you after the break. But we don't know why. We can't tell what's different about these different studies that is leading to the differences. We can make some hypotheses and then do some exploration, but we have no sense going in what the important differences might be. And in the third situation, we basically have a hypothesis ahead of time about what's going to cause the treatment to be more effective in some situations than others, and therefore we can make a priori ahead of time, plan an analysis on subgroups or planned regression analyses where we're looking at what we think are going to be important study characteristics that are covariates of effect size. Am I using any terms that people are unfamiliar with? Okay. In the social sciences, we tend to say moderator variables, and in health sciences, we seem to talk about covariates more. So I always try to make sure I'm using the right term. Okay, so I want to show you the 3 different contexts as a way of setting up how we're going to talk about actually going about doing the meta-analysis, and then later on to talk about heterogeneity and how we actually detect it, as opposed to just showing you graphics of it, and then further on how to choose whether to do a fixed effect or a random effect, and what that means for both your analysis and your interpretation of your results. So when the treatment effect is actually consistent, meta-analysis will give you a more precise estimate of the mean. Okay? And since the treatment's consistent, the mean in this case is a good spokesperson for all of the data. Okay? And for that, I'm going to look at the streptokinase review. This is a very classic. You'll see it in lots of courses on meta-analysis. In this case, there were over 30 studies. Okay? And the question was, does streptokinase reduce death from stroke? Stroke? Heart attack. Heart attack, right, yeah. Okay. And if we look down here at the bottom, we can see that the analysis tells us that yes, there's about a 25% difference in the odds of dying, depending on whether you got streptokinase or not. But if you look at the component studies, they look, what, all over the place? Yeah, all over the place. They're actually sorted in chronological order. They look less all over the place if I showed you them sorted by effect size, but okay, these are in chronological order. And the first one was done in 1963. The meta-analysis was done in 1989 and 1990. Okay. And the p-value again is wrong because it says 0. Okay, but we have a fairly narrow confidence interval around our estimate of the mean effect. It can be as low as 0.72 or as high as 0.82. That's pretty precise as far as most research estimates go. So in basic analysis, we saw that, or you didn't see yet, the treatment effect was consistent, the combined effect was substantial, but only 6 of these 33 studies on their own reached a statistically significant effect. Okay? Now, what I want to show you, and this is, again, what I think is a wonderful feature of meta-analysis, by 1977, first, let me back up. This is what's called a cumulative meta-analysis. A cumulative meta-analysis starts with the first meta-analysis, and then it adds them sequentially as they were done. So the second line represents the first 2 meta-analyses, the third line represents the first 3 meta-analyses, and so forth. By the time we get to about the 14th or 15th study, around 1977, we can see that the effect size has really pretty much stabilized. I would actually argue that it pretty much stabilized by around the 5th study, but okay, let's be a little conservative here. That in 1977, we reached a combined effect of 0.747, and by the time we got to 1988, the combined effect was about 0.7 7. Okay? But I guess here, by this point, it's clearly significant, although again, by the time we had 6 studies, it was statistically significant, and also 0.748, so maybe we would have even wanted to do a meta-analysis then. But in fact, being even very conservative, meta-analysis done in 1977 would have been definitive by anybody's standards. Okay, 47,000 patients were randomized in those other 18 studies or so that I showed you, right? So half the people were assigned to a treatment that wasn't, people in the control group didn't get a treatment that we should have known was affected by them, right? There are just millions of people who weren't in the clinical trial, who had, who needed or who were candidates for the medication. And there was a narrative review done in 1992, which was actually more or less contemporaneous with this meta-analysis, where they're still saying that definitive results aren't in. Okay? So if you think about the number of lives that would have been saved by, even with a high NNT, a lot of people get heart attacks. The number of people that had been saved if meta-analysis had been around in 1977, didn't exist yet really, it was just first being developed. It really can give you a lot more powerful and clearer results than a narrative review, because the narrative review is going to focus on the fact that only 6 of the 33 studies met the criteria for statistical significance. Okay? So I hope this persuades you why meta-analysis is an important tool to have in your methodological research toolbox. Okay, let me show you another meta-analysis where essentially we do have a more powerful estimate of the mean, but where maybe the mean isn't such a good indication of what's really going on, because there seem to be differences across the studies in their effect that we can't attribute to just chance variation. Okay? So when we're looking at heterogeneity in a meta-analysis, our key task is to decide what is essentially noise created by sampling error and what's essentially a signal with studies saying, look at me, I'm different, look at me, look at me. Okay, so we need to separate the noise from the signal, and that's not always so simple. Okay. So what I'm going to look at for my second example is a study on the prevalence of post-traumatic stress disorder in parents of children with severe illnesses. Okay? Basically, let me show you. This is what the forest plot looks like. You can see that each of the studies, except for this one over here, was itself statistically significant. And you can see by the fact that they have short confidence interval bars that they don't overlap so much with each other. When you see this kind of non-overlap, okay, you have a sense that, in fact, there are real differences across the studies in the effect, and in this case, in the incidence of PTSD. So if you just look at the event rate from the observed event rate in each study, okay, they range from 0.05 in the Manny study from 1998 to 0.40 in the Fummler study from 2001. Okay, our heterogeneity tests, I will go into the technicalities of that after the break, but the heterogeneity tests told us that most of the variation, most of the variation across studies is actually real. It's not due to chance. After we clear out the bumping around that we would expect from sampling, there's still a lot of difference, and that the prevalence, the authors note and kind of end their study with the precedence varied from 5% to 40% across the studies, and they didn't really investigate potential reasons for that heterogeneity. Since they hadn't hypothesized any reasons, all they could really do afterwards would be some post hoc exploratory analysis. They can't really create hypotheses after having these results without any money down on the table before the study about what possible covariates could have had an effect. Although doing a little exploratory analysis to form a hypothesis for a future study might not have been a bad idea. It could have been the ages of the kids, it could have been the nature of the illness, it could have been whether the kind of support the parents got, lots of different things, but they didn't really look at that. Okay. The final kind of reason for meta-analysis I would want to look at is when we do have ahead of time hypotheses about what might make the effects differ from study to study. And in that case, we can actually, if we want to, I just want to make sure that you realize that in this case, all I would be comfortable saying is that, yes, PTSD is a problem for parents of clinically ill children, but I can't tell you what makes it better or what makes it worse based on my meta-analysis, okay? Because the mean is not necessarily a good representation of each study, right? If you vary from 0.05 to 0.40, what does 0.18 tell you? Okay? But if we're interested in looking at subgroups, we can do an overall meta-analysis, or we can proceed directly to looking at the subgroups of interest to us and see whether those subgroups actually influence the treatment effect. Okay, in this case, I want to look at the impact of two different drugs on weight loss, one called orlistat and one called sibutramine. They have different mechanisms of operation inside your gut, although they are both promoted by their respective drug companies that develop them, drug companies can turn anything into an illness. That's just an aside. We can kind of see the hypothesis was that because of the way it worked, that sibutramine would have a stronger effect on weight loss than orlistat did, and the subgroup analyses support that. Sibutramine had an effect of a risk difference of 0.32, and orlistat had 0.21. Overall, the effect was 0.24 because there were more orlistat studies than sibutramine studies in the analysis. Okay, but you can see, even if we didn't have the two subgroup means, that even if we just lay them out this way, you can kind of by eyeball see differences in the two subgroups. So both drugs were effective. Sibutramine was somewhat more effective than the orlistat. And if you are interested in where the side effects, they both have very nasty, not life-threatening side effects, but like orlistat, you can't necessarily control when you're going to move your bowels, and so you probably have to be pretty desperate to lose weight over there. But here we were able to show, and if you did a statistical significance test, you would find that there was a statistically significant difference in the amount of weight loss produced by orlistat compared with sibutramine. And here's a slightly different mini forest plot, which essentially just shows you the subgroup means rather than each of the component studies going into them. And this is where we actually did an ANOVA type of test, but for meta-analysis, comparing the two different means, and the difference in the mean for each of the two drugs was statistically significant at the 0.001 level. And we'll get back to some of this stuff later, but don't obsess about it now if you don't, if it doesn't speak to you. Okay, so I want to point out also that outcomes matter. So in this particular case, one would assume that before the study, the meta-analysis was conducted, that the outcome of interest was in fact the one they reported, which was weight loss. But if, for example, they do have different side effects, different contraindications, and so forth. If we had looked at one of these other outcomes as our main outcome of interest, we might have a very different looking meta-analysis. And one of the things that I'm not going to talk about, but I'm just going to throw it out there for you to think about, is that one of the questions that we need to answer when we're collecting primary studies to go into a systematic review is whether it's possible that they selectively chose outcomes to report based on making themselves look good. So that if they had, let's say they actually collected data on 4 different outcomes, weight loss, patient satisfaction, some specific side effect, and some adverse effect, and they find that, for the sake of argument, sibutramine causes better weight loss, but it also has more side effects, and they decide to pretend that all they were looking at was weight loss. That's actually very common, unfortunately. And protocols are supposed to save you from doing that, and the protocols in the original study, what you file with your IRB, it's supposed to have all the outcomes. When meta-analysts who are interested in selective reporting go back and actually compare published articles with protocols, they find that in many cases outcomes are actually chosen to be reported selectively. And clearly that's problematic. But it's not problematic for the meta-analysis, it's problematic for the way we report science in public. But outcomes matter, and just because you find that a drug is better for a particular outcome doesn't mean that you should conclude anything else about any other outcomes. Okay. I also want to show you this one, caffeine as an analgesic adjuvant, add-on, for acute pain in adults. When I was a kid growing up, there was this drug called Anacin, and they had lots of commercials about it. I don't know what name it went by in Croatia, but essentially it was Tylenol plus caffeine. Okay, and they had doctors on TV telling you that that is the #1 headache remedy that they recommended. Well, this meta-analysis basically asked, overall, does adding caffeine to either ibuprofen or paracetamol, which we call the main brand in the States is Tylenol? Well, the answer is yes, it actually does make a difference. Adding caffeine provides more relief than the plain paracetamol, ibuprofen. However, it seems to really rev up ibuprofen a lot more than it revs up Tylenol. So the Anacin doctor on TV was wrong. He misrepresented his drug. But you can see also here that there seems to be more heterogeneity around the effect well, no, that's not true. There seems to be less precision around our estimate of the ibuprofen effect than the Tylenol effect, but they pretty much still don't overlap. So, and if you did the significance test, you'd see that it gave statistically significantly more extra effect for the ibuprofen and for the paracetamol. Just some other examples of, I'm trying to give you examples of types of covariates you could look at, as well as types of effect sizes that can be used. So in this particular case, we looked at prevalence with no moderators, no covariates in the analysis. In this case, we're looking at risk differences where the actual treatment differed, drug of choice differed. In this case, we're looking again at differences in the degree to which two drugs are affected by the addition of caffeine. In this particular case, we're going to be looking at type of patient as the moderator. So we're looking at whether statins' effects differ depending on whether the person smoked or not. I don't know what the clinical background or the hypothesis that it would make a difference is, but apparently there was one. And you can see that the difference in the effect for smokers and non-smokers was different. And again, that's a statistically significant difference. So that overall the statins were able to have an effect, but they seem to have more of an effect for smokers. And maybe one of you can explain the clinical mechanism for that to me, but I don't know. Okay. They also did an effect by gender analysis. Often people these days try to look at gender as a moderator, as we learn more and more about the fact that some treatments just seem to work differently for men and for women. Limited sometimes by the fact that a lot of studies have been done only on men. But anyhow, the bottom line here is that if you're interested in a very narrow question where you anticipate consistent effects, you want to limit your inclusion criteria to studies that were as similar as possible so you can get the best possible estimate of the effect that they share and also test to make sure that it's really consistent. You can include studies that just are randomly variable that all ask the same general question and get a sense of the range of variability of the actual effects. That might be helpful if you want to just make sure that the treatment that you're recommending isn't going to harm anybody. So in that case, it might be, if that wasn't a prevalence estimate for PTSD, but a degree of relief from PTSD, then you might make a cost argument that if it had a small reduction, like 0.04 less PTSD, it wasn't worth it, and for 0.40 it would be worth it. But if you just wanted to make sure you weren't harming anybody with your treatment, as long as you could show that PTSD went down based on your treatment, you would say, well, yes, there's a lot of heterogeneity, but there's no case in which the effect is in the opposite direction, so I'm okay with it. Or you might say, well, the size matters, and the sizes here are very variable, so I don't want to make any recommendations right now. We really do need to do further research. Or you can look at a broad variety of studies that vary in ways that you think ahead of time will matter for the effectiveness of the treatment, and then you can actually examine the impact of those factors, both in terms of different means and in terms of whether it reduces your estimate of true variation. So think ANOVA, So if the subgroups are much less variable than the overall analysis, as well as the means being different, you're in a good place because you've explained a lot of why the effect's there. Okay. Okay. So I think the last thing that I'm going to mention here is when you are looking for subgroups or looking for covariates, you can't just go on a fishing expedition. You can't just say, oh, I think, I have 20 studies, and here are these 10 covariates that I think might make a difference. I think it's going to depend on the age of the participant, the gender of the participant, whether the study was done in a teaching hospital or not, whether it was done on chronically ill people or just somebody with a first episode of something. Because if you throw all of those variables into your analysis, something's going to come up just by chance. So you really are going to make type 1 errors finding something that doesn't really exist if you do too many moderator analyses. Lately, the suggestion is somewhat similar to regression analyses in primary studies, which is maybe look at one covariate for about every 10 studies in your analysis. Some people will say, but I only have 10 studies, and I have these 2 factors that I want to look at. Well, you could look at them, but just be aware that you might not have that much power in that situation. The other thing is that when you're doing an analysis of covariates, very often covariates are correlated with each other or confounded with each other. So, and in that case, it's kind of hard to tell which of the factors is actually driving the difference in effect sizes. So, for example, I did a meta-analysis on stress management interventions in the workplace, and we found that cognitive behavioral interventions were much more effective than journaling or breathing exercises. And we also found that longer interventions were better than shorter interventions. But we also found that cognitive behavioral interventions was correlated with intervention length. So it's hard to tell in that case whether we should say, well, it's the CBT, the nature of the intervention itself, or the length of the intervention that was actually influencing the effectiveness of the intervention. So when you have enough studies, you can unpack the moderators into smaller subgroups, like cognitive behavioral interventions that were short versus cognitive behavioral interventions that were long. In most meta-analyses, you don't have that many studies to be able to do that kind of subgrouping in a rigorous manner. So just be careful when you're reporting results to make sure that you're not ignoring correlations among covariates. And the final thing that I want to say, that even if you're doing a meta-analysis on only randomized controlled trials, so that on the primary study level and on the level of your overall effect, you can make a causal claim about treatment, any of the covariate analyses are observational analyses. You're looking at them at the study level, and studies were not randomized to gender or to length of intervention or any of those things. So bear in mind that you can't really make a causal inference, only a correlational claim on the basis of any of your moderator analyses, unless in the rare case where actually a covariate was included in the randomization procedure identically across all of the studies that went into your analysis. We have about 7 minutes left before our break, so I'm going to ask anyone who has any questions to please